The year is 1880. The place is a farm near Sandefjord, Norway. The farm is called Gokstad. For generations, people had pointed to a large mound on the property. They called it Kongshaugen, the King's Mound. Local legend said a king and his treasure were buried there. The sons of the farmer who owned the land decided to find out. They started digging into the mound more for fun than anything else. They didn't get far before their shovels hit something hard. It wasn't rock, it was dark, solid wood. Word spread. Soon, an archaeologist from the University of Christiania, now Oslo, arrived. His name was Nicolason. He took over the excavation. The work was slow. They weren't digging for treasure. They were uncovering a story. Well, what emerged from the wet, blue clay was not just a pile of wood, it was a ship. A nearly perfectly preserved Viking ship. Buried around 890 AD, it had been sealed in an airtight tomb of clay, protected from the rot of centuries. As Nicolason and his team carefully cleared the dirt, they started to see things that made no sense according to the shipbuilding knowledge of their time. The hull was made of overlapping oak planks. They were held together with thousands of iron rivets, hammered in from the outside and secured on the inside with a small square metal plate. This was clinker construction, but it was the ship's backbone, the keel. That was the real puzzle. It was carved from a single, massive piece of oak. It was surprisingly shallow, allowing the ship to navigate in water only a few feet deep. But it was also flexible. The way the planks were attached to the ribs, and the ribs to the keel, wasn't rigid. The ship was built to move. It was designed to twist and bend with the power of the North Atlantic waves. A modern ship of the 19th century was built to be a fortress, to fight the sea with brute strength and rigidity. If a wave was too strong, the ship would break. The Gokstad ship was different. It was designed to dance with the waves. The flexible keel and the overlapping planks allowed the entire hull to deform, to absorb the energy of the ocean and flow with it rather than fight it. The ship didn't break because it bent. This was the first secret uncovered from the King's Mound. It was an engineering principle so advanced and so counterintuitive that it had been lost to time. And it was just the beginning. Number 15A ship's frame was born, not built. Halston stood at the edge of the forest, his hand resting on the rough bark of an old oak. It was the year 875 AD, near the fjord of Kaupang. He wasn't looking for straight timber. Any fool could find a straight tree and cut it into straight planks. Halston was a shipwright. He was looking for the bones of a ship. His apprentice, a young boy named Finn, followed him, his eyes wide. Finn thought they were here to cut down trees for the new longship commissioned by the Jarl. He expected to hear the sharp bite of an axe into a tall, straight trunk. Instead, Halston walked past the straightest, tallest oaks. He led Finn deep into the woods, to the places where the trees had struggled. He pointed to a tree that grew near a large boulder, its main trunk forced to curve dramatically to reach the sunlight. He ran his hand along the curve. "Her!" Halston said, his voice low and gravelly. "This is a rib." Finn was confused. A rib was a part of the ship's internal frame, the curved pieces that gave the hull its shape and strength. They were supposed to be carved. Halston shook his head. Carving a rib from a straight piece of wood is an invitation to the sea gods to take your ship, he explained. He knocked his knuckles on the curved trunk. When you saw a curve into a straight piece of wood, you cut across the grain, you sever the fibers that give the tree its strength. It's like cutting the muscles in a man's arm. The shape is there, but the power is gone. He then showed Finn a different tree. A massive branch grew out from the trunk at a near-perfect right angle. It was thick, gnarled, and looked immensely strong. "That is a bite," Halston said. He was referring to the crucial L-shaped piece of the frame that connects the hull to the crossbeams. The tree spent 100 years perfecting that shape. It grew that way to support its own weight against wind and snow. Who are we to think we can make something stronger by cutting and joining two separate pieces of wood? The tree has already done the work. This was the secret. Viking shipwrights didn't just see trees as a source of lumber, they saw them as a collection of pre-existing parts. And they would wander the forest for days, not just looking for oak or pine, but for specific shapes. They needed knees, ribs, bights, and stems. These were the structural components with complex curves and angles. Instead of fabricating them in a workshop, they harvested them directly from nature. They looked for trees with natural crooks and bends where the wood grain followed the curve. This meant the internal structure of the wood, its long cellulose fibers, remained unbroken. The resulting frame piece was exponentially stronger and more resilient than one cut from a larger block of straight-grained wood. Finn watched for weeks as Halston and the other men brought these strange, crooked pieces of wood back to the building site. They looked like a pile of driftwood, a chaotic mess of natural shapes. But then Halston began to lay them out. He chose a long, straight oak for the keel. Then he began to fit the pre-shaped ribs. It was like a puzzle. A rib from one tree fit perfectly against a section of the hull. A knee joint from another locked a crossbeam in place with unyielding strength. The ship grew organically. It wasn't an assembly of cut and measured parts. It was a careful integration of natural forms, each chosen for its inherent strength. This process took immense skill and patience. It required a shipwright to hold the entire design of the ship in his head while walking through the forest. He had to see the finished rib in the living tree. This method also saved an enormous amount of labor. Carving a large curved frame piece from a solid block of oak with simple hand tools was a monumental task. By finding a piece that was already 90% of the desired shape, the shipwright only needed to finish it with his adze, trimming it to fit perfectly. It was efficient, it was strong, it was a partnership with the forest. The ship that rose on the shore was not just a product of human hands. It was a product of the forest itself, its strength rooted in the 100-year struggle of the trees it came from. The frame was born in the wild, not just built on the beach. Number 14. The nails that pulled the ship together as they cooled. Ingrid was a blacksmith's daughter. Her world in the year 910 AD in the settlement of Birka was one of fire, soot, and the rhythmic clang of hammer on iron. Her father, Stig, was not a swordsmith. He did not forge axes for warriors. He made nails, or more accurately, he made rivets. Hundreds and thousands of them. For the longships that were the lifeblood of their community, Ingrid, who was only 12, was learning the craft. Her job was to work the bellows, keeping the charcoal fire roaring at a bright, almost white heat. Today, they were making rivets for a new ship, a carvey being built for a local merchant. Stig pulled a long iron rod from the fire. It glowed with an angry orange light. He worked quickly. With a few skilled strikes of his hammer, he formed a mushroom-shaped head on one end of the rod. Then, using a chisel, he cut a length of about 10 centimeters. He dropped the glowing piece into a bucket of water where it hissed and steamed. This was the rivet, the pin that would hold the ship together. But it was only half the story. Ingrid's other job was to make the roves. These were small, diamond-shaped pieces of iron, thinner than the rivet. She would take a flattened piece of iron and, using a punch, create a small hole in the center. She made hundreds of these, her small hands surprisingly deft with the heavy tools. She didn't fully understand their purpose until a shipwright named Kettle came to the forge. He needed to repair a damaged plank on an old ship. He asked Ingrid to bring a small brazier of hot coals down to the shore. At the ship, Ingrid watched, fascinated. Kettle and his apprentice had fitted a new oak plank, its edge overlapping the one below it. They had drilled a small hole through both planks. The apprentice then took one of Stig's rivets and heated its tip in Ingrid's brazier until it glowed red. He pushed the hot rivet through the hole from the outside of the hull. The mushroom head sat flush against the outer plank. Inside the ship, Kettle took one of Ingrid's roves and slipped it over the hot, pointed end of the rivet. It was a snug fit. Then came the magic. Kettle held a heavy piece of iron, a dolly, against the rivet head on the outside of the ship. Inside, the apprentice began to hammer the hot, protruding tip of the rivet. He spread the metal, hammering it flat over the rove, creating a second head. This process was called peening. The rove acted like a washer, preventing the new head from pulling through the soft wood. But their real secret was something Ingrid couldn't see. It was something she could only feel later. Kettle explained it to her as they worked their way down the plank. The iron is hot when we hammer it, he said, his voice muffled from inside the hull. What happens to iron when it cools? As Ingrid knew this from the forge. It shrinks, she said. Exactly, Kettle replied. The rivet is hammered tight when it is hot and expanded. As it cools, it shrinks. It tries to pull itself shorter. He pointed to the line of freshly hammered rivets. Every single one of these is now pulling with immense force. They are squeezing the two planks together tighter than any man could with his hands. They don't just pin the wood, they bind it. They make two planks into one solid piece. Later, Ingrid placed her hand on the inside of the hull. She could feel the cold iron of the newly clinched rivets. There was no give, no space between the planks. The hull felt like a single piece of carved wood. She understood now. Her father didn't just make nails, he forged the source of the ship's strength. Each rivet was a tiny, powerful clamp, multiplied by the thousands needed for a single longship. Sometimes as many as 7,000 for a large one. They created a hull that was both incredibly strong and surprisingly light. The iron wasn't just a fastener, it was an active component of the ship's structure in a state of constant tension, holding the vessel together with a force applied at the moment of its creation in fire and hammer strikes. Number 13, the woolen tar that made the skin breathe. Asa hated the smell. It was a thick, pungent odor of pine tar and sheep's wool that clung to her clothes and hair for days. She was working with her mother, Sigrid, on the final stages of a new longship in the year 950 AD on the coast of Denmark. The ship was finished, its bare oak planks gleaming in the weak sunlight. But it was not yet ready for the sea. It needed its skin. The men had already done the heavy work of riveting the planks. Now it was the women's job to make the ship waterproof. This process was called caulking, but it was nothing like the caulking methods used centuries later, where fibers were hammered violently into the seams. The Viking method was far more subtle and far more effective for their type of ship. Asa's job was to prepare the cord. She took raw, greasy wool, full of natural lanolin, and spun it into a thick, loose yarn. It wasn't the fine yarn used for clothing. This was coarse and heavy. She worked alongside other women and older children, their hands moving rhythmically, twisting the fibers into long, snake-like ropes of wool. Meanwhile, Sigrid supervised the heating of the tar. It was a black, sticky substance rendered from the roots of pine trees. The process took days, slowly cooking the wood in a sealed clay oven until the resinous tar dripped out. The tar was heated over a low fire until it was a liquid bubbling slightly. The smell was overpowering. The secret was in how these two materials were combined and applied. Care, the master shipwright, showed Asa exactly where the wool cord needed to go. It wasn't stuffed between the planks. That would force them apart. Instead, it was laid gently in the overlap of the clinker-built hull. As a new plank was laid over the one below it, a groove was often carved on the inside face of the upper plank. The tar-soaked woolen cord was pressed into this groove. When the planks were then riveted together, the cord was compressed, creating a flexible, watertight seal. Asa watched as her mother took a length of the wool yarn and submerged it in the hot tar. She used 2 sticks to pull the dripping black cord out and pass it to the shipwrights. They quickly laid it in the seam of the next plank to be attached. The process was repeated for every single seam on the ship, from the keel to the gunwale. Why wool? Asa asked her mother one day, wrinkling her nose at the smell. Why not just fill the cracks with tar? Sigrid paused, wiping her sticky hands on a rag. Because a ship is not a dead thing, she said. It moves, it breathes, especially our ships. She explained that the Longship's hull was designed to flex in the waves. A rigid sealant, like pure pitch or resin, would crack and break away as the hull twisted. The ship would leak and eventually founder. The wool is different, Sigrid continued. She picked up a piece of the raw wool. It is springy. It is full of oil from the sheep. When it's soaked in tar and pressed between the planks, it stays flexible. She squeezed the wool and it bounced back. When the ship twists in a storm, the wool seal twists with it. When the wood swells in the water, the wool compresses. When the wood dries and shrinks in the sun, the wool expands to fill the gap. It is always moving, always keeping the sea out. This was the genius of their method. The tar provided the waterproofing, and the wool provided the flexibility and longevity. The natural lanolin in the wool also helped to repel water and prevent rot. This combination created a dynamic seal that worked in harmony with the ship's flexible design. It allowed the ship to remain watertight even as its planks shifted and moved in rough seas. It wasn't a simple case of plugging a hole. It was about creating a living, breathing skin for the vessel, one that could adapt to the constant stresses of the ocean. The foul-smelling, sticky work that Asa hated was one of the most critical engineering secrets of the Longship. Number 12. The floorboards were designed to be ripped up in a hurry. Sven crouched low in the bilge of the sea serpent. The air was thick with the smell of wet wood, tar, and the unwashed bodies of the 30 men around him. They were caught in a sudden storm off the coast of Northumbria in the year 866 AD. The waves were not massive, but they were steep and chaotic. Water was coming over the sides, sloshing around their ankles, but that wasn't the main problem. The ship had sprung a leak. Somewhere along the keel, a seam had opened under the relentless pounding of the waves. The ship's commander, Ivar, shouted an order. "Find the leak, bail!" The men worked in a frantic yet practiced rhythm. Several men grabbed large wooden buckets and began bailing, their movements synchronized to the roll of the ship. Sven's job was different. He and another man, Olaf, were responsible for the floor. The floor of the Longship wasn't a permanent fixed deck. It was made of loose wooden planks called tilja. These boards rested on the lower parts of the ship's ribs, creating a flat surface for the crew and their cargo. Underneath these floorboards was the bilge, the lowest part of the ship where water collected. Crucially, the floorboards were not nailed or tied down. They were cut to fit snugly, but they could be removed in seconds. Sven grabbed the edge of a board and ripped it up. Olaf did the same with the one next to it. Within moments, they had opened up a large section of the ship's floor, exposing the ribs and the keel below. The sloshing water was deeper here, and they could see it gushing in from a spot near the mast. "Hair!" Sven yelled, pointing into the churning water. This was the design's hidden purpose. In a crisis, the crew needed immediate access to the entire inner surface of the hull. A leak couldn't be fixed if you couldn't get to it. The removable floorboards meant that any part of the hull could be exposed and repaired, even in the middle of a storm. It also made bailing much more efficient. Instead of trying to scoop water from a shallow, widespread area on top of a deck, the men could open the floor and bail directly from the deep pool of water collecting around the keel. With the leak located, the next stage of the plan went into action. Another crew member, Eric, pushed a large bundle towards Sven. It was a wad of tar-soaked wool and animal hides. Sven took a deep breath, plunged his arms into the icy seawater, and felt for the split in the planks. He forced the wad of material into the gap from the inside. The pressure of the seawater on the outside of the hull helped to push the plug into place, slowing the torrent of water to a trickle. It was a temporary fix, but it would hold until they could make landfall and properly repair the plank. While Sven held the plug, other men continued bailing. With the leak slowed, the bailing started to gain on the incoming water. Slowly, the water level in the bilge dropped. Once it was under control, Sven and Olaf replaced the floorboards. The deck was restored. Cargo, mostly chests of supplies and weapons, had been designed to sit on top of the floorboards and could be quickly shifted out of the way. The entire operation, from Ivar's first command to the floorboards being back in place, took less than 10 minutes. The engineering secret here was not a complex mechanism, but a simple, practical design choice. The ship was built with the expectation of taking on water and sustaining damage. The loose floorboards were a key part of the ship's damage control system. They acknowledged the reality of sailing in the treacherous North Atlantic. It meant the ship could be, in a sense, field stripped and patched up by its own crew while underway. It turned the entire crew into a responsive repair team and made the vessel far more resilient than a ship with a sealed permanent deck. Number 11. The steering oar was smarter than a rudder. Bjarni gripped the tiller of the steery, the great steering oar of his ship, the Wave Runner. It was the summer of 985 AD, and they were navigating the treacherous coastal waters of a land he had only heard stories about, a place he would later call Vinland. The water was shallow, filled with hidden rocks and unpredictable currents. A conventional stern-mounted rudder, like those he had seen on some southern trading ships, would have been a liability here. It would have been smashed to pieces on the first hidden rock. The steery was different. It was not a rudder. It was a massive, specially shaped oar mounted on the steerboard side of the ship, near the stern. It was attached to the hull by a single, robust pivot point, a large, cone-shaped block of wood on the outside of the hull, often called a wart. A thick leather or rope strap passed through the oar and the hull, holding it in place but allowing it a huge range of motion. As they moved through a narrow channel, Bjarni's forward lookout shouted a warning. A dark shape loomed under the water just ahead. A rock. With a conventional rudder, turning sharply would have been slow. The rudder would have acted as a brake, killing their momentum. But Bjarni wasn't using a rudder. He shoved the tiller hard to port. The blade of the huge oar, deep in the water, angled sharply. It didn't just redirect the water flow, it acted like a pivot. The stern of the longship swung out powerfully while the bow carved a tight turn. They missed the rock by a hand's breadth. The ship's momentum was barely affected. This was the first secret of the styriate's efficiency. Because of its shape and position, it had incredible turning authority. A small movement of the tiller produced a large and immediate response from the ship. It could make the long, slender ship turn almost in its own length, a maneuverability that was crucial for navigating narrow fjords, beaching the vessel, or for tactical advantage in a sea battle. A little later, the water became dangerously shallow. Bjarni gave a command. A crewman loosened the rope that held the steery in place. By pulling the tiller upwards, Bjarni could raise the entire oar, lifting its blade clear of the shallow bottom, where they could navigate in water barely deep enough to float the ship without fear of damaging their steering mechanism. And once they were back in deeper water, the oar was lowered again. This adjustability was impossible with a fixed rudder. It allowed the Longship to explore and operate in waters completely inaccessible to other vessels of its size. But the styry had another, more subtle secret. It provided feedback. Bjarni could feel the water through the tiller. As he held it, the vibrations and pressures transmitted up the massive wooden shaft told him exactly what the water was doing. He could feel the change in current, the turbulence that hinted at a submerged obstacle, the way the ship was responding to the wind and waves. It was a direct tactile connection to the sea. A helmsman with a rudder feels the mechanics of the ship. Bjarni felt the ocean itself. He could steer by feel as much as by sight, making constant, tiny adjustments that kept the ship perfectly balanced and on course. The styry was not a primitive rudder. It was a highly sophisticated hydrofoil, perfectly adapted to the design of the Longship and the needs of its sailors. It was powerful, responsive, adjustable, and intuitive. It required great skill and strength to operate, but in the hands of an experienced helmsman like Bjarni, it was a far superior piece of engineering for the kind of sailing the Vikings did. It was a tool that allowed them not just to steer their ship, but to feel their way across the world. Number 10. The sail was a simple square, but it was a high-tech engine. Thora stood on the shore, her eyes fixed on her husband's ship as it prepared to leave the fjord. It was 930 AD in western Norway. The ship, a small trading gnar, was similar in construction to a longship but wider and deeper for cargo. The crew was raising the sail. It looked simple enough, a huge single square of wool, but Thora knew the truth. That sail was the product of a year of her life, and it was one of the most advanced pieces of technology they owned. The secret of the Viking sail began with the wool. It couldn't be just any wool. It had to come from a specific breed of sheep, the Old Norse sheep, whose fleece had 2 layers. There was a soft, fine inner layer and a long, coarse, water-repellent outer layer called the tog. When Thora and the other women of the village spun the yarn for the sail, they had to carefully separate these fibers. The yarn for the warp, the strong vertical threads on the loom was spun tightly from the long, coarse tog fibers, with a little of the fine wool mixed in for body. The yarn for the horizontal threads was spun loosely, mostly from the soft, oily inner fleece. Weaving the sail was a massive undertaking. A loom big enough had to be constructed, often outdoors or in a special longhouse. The weaving itself was slow, hard work. Thora had to beat the weft threads down with a heavy wooden batten, packing them so tightly that the finished cloth was almost rigid. The result was a fabric with unique properties. The tightly packed, oily weft threads of soft wool made the sail dense and water-resistant. The strong, taut warp threads of coarse wool gave it incredible strength to withstand the force of the wind. But a plain woven sail wasn't enough. The woolen cloth, for all its clever weaving, was still porous. It would stretch when wet and let the wind pass through it. The next stage was to finish it. Thora and her helpers would lay the massive sail, which for a large ship could be over 100 square meters, on the ground. They would then work a foul-smelling mixture into the fabric. It was a slurry of horse grease, fish oil, and ochre. They rubbed it into the weave with their hands and with smooth stones, saturating every fiber. This coating did two things. Again, it made the sail virtually waterproof, so it wouldn't get heavy and stretch in the rain, and it sealed the remaining pores in the cloth, making it non-porous to the wind. All the wind's energy would now be captured to push the ship forward. The final piece of engineering was the complex network of ropes stitched onto the sail itself, called the bolt rope. This reinforced the edges and crisscrossed the sail's surface, distributing the strain from the wind evenly across the fabric and preventing it from ripping. Thora also wove a series of reefing points into the sail short ropes that allowed the crew to tie up a portion of the sail at the bottom, reducing its size in very strong winds. This was a critical safety feature. As Thora watched the crew hoist the sail, she saw her year of work rise into the sky. The deep red and white striped pattern, colored with mineral pigments mixed into the grease, was her signature. The sail was not a simple sheet. It was a carefully constructed airfoil. It was light enough to be managed by a small crew, yet strong enough to power a 20-ton ship across the Atlantic. Its wool and grease construction was perfectly suited to the wet, cold climate of the north. It was an engine made of wool, and it was the key that allowed the Vikings to travel farther and faster than anyone before them. Number 9. The mast could be raised and lowered in minutes. Leif stood bracing his feet on the deck of the Ocean Strider, a sleek longship slicing through the waters of the Baltic Sea in 1015 AD. They were on a trading mission, but in these waters, a trading mission could become a raid, and a raid could become a battle in the blink of an eye. For the past 3 days, they had been sailing under the power of their great square sail, the wind pushing them steadily eastward. But now, their destination, a small river mouth, was in sight. The wide open sea was giving way to a narrow, winding river. The wind here was unreliable, blocked by hills and forests, and a tall mast would be a liability, easily caught in overhanging branches. The ship's captain, Magnus, gave the order down mast. There was no panic, no complex preparation. The crew moved with a swift, practiced efficiency. The entire system was designed for this moment. The mast itself was not set in a deep, permanent socket like in other ships. It rested in a simple step block on the keel at the bottom, but its main support was a massive block of oak at deck level called the mast partner or mast fish. This block was huge, spanning several ribs, and had a U-shaped channel carved into it where the mast rested. Crucially, the aft end of this channel was open. Leif and 3 other men went to the mast. They untied the stays, the heavy ropes that ran from the top of the mast to the sides of the ship, which kept it from falling sideways. Other men stood ready at the backstay, the rope that kept it from falling forward. The captain gave another shout. The men at the backstay let it go slack. Leif and the others gave the mast a powerful shove forward. The base of the mast, sitting in its keel step, acted as a pivot. The mast tilted. Then the genius of the mast fish came into play. A large wooden wedge that locked the mast in place at the front of the mast partner was knocked out. With the wedge gone, the men could simply push the entire mast backwards. It slid out of the open-ended mast partner and, under control of ropes, was lowered gently to rest in a specially designed cradle at the stern of the ship. The entire process, from a fully rigged sailing vessel to a sleek, low-profile rowing boat, took less than 5 minutes. The massive mast, which could be up to 15 meters tall, was now lying securely along the center line of the ship, out of the way. With the mast down, the ship's character changed completely. Oars were run out through the oar ports. The Ocean Strider was now a fast, agile rowing vessel. They could navigate the tight turns of the river with precision. They could glide silently into a settlement without the telltale shape of a sail giving them away from miles off. You know, they could pass under low bridges or branches. You know, this ability to switch from a high-performance sailing vessel to a high-performance rowing vessel was a massive tactical advantage. Later, as they left the river and re-entered open water, the process was reversed. The mast was walked upright, with men pulling on the forestay. It was slid back into the U-shaped mast partner, the wedge was hammered back into place, and the side stays were retightened. Within minutes, the sail was unfurled, and the ship was once again a creature of the wind. This system was a masterpiece of practical engineering. It recognized that a ship needed to be versatile. The mast was not a permanent fixture, but a modular component of the ship's propulsion system. The combination of the simple keel step, the clever open-ended mast fish, and the system of wedges and ropes made what should have been a major undertaking into a routine, everyday task. It allowed the Vikings to use their ships in a way no one else could, seamlessly transitioning from open ocean sailing to coastal and riverine infiltration. Number 8. The ship was built light on purpose. Ragnar, the shipwright, ran his hand over the freshly carved oak plank. It was for a new longship, a skeed, destined for the fleet of a powerful jarl. It was the year 890 AD. In the shipbuilding yards of Roskilde Fjord, the plank was remarkably thin. For a ship nearly 30 meters long, the hull planks were a little more than 2.5 centimeters thick, about an inch. A visiting merchant from the south, a man used to the heavy fortress-like ships of the Franks, had scoffed at it. "You build your ships from eggshells," he had said. "A single large wave will break it in two." Ragnar had simply smiled. The man did not understand. The lightness of the ship was not a weakness. It was its greatest strength. Every single element of the ship's design was geared towards achieving this lightness without sacrificing strength. It started with the way the planks were made. They were not sawn from a log. They were split radially from a massive straight-grained oak. This technique, called cleaving, followed the natural grain of the wood, keeping the long wood fibers intact. A sawn plank has its fibers severed where the saw crosses the grain, making it weaker. A split plank was far stronger for its thickness. This meant Ragnar could make the planks much thinner and lighter while retaining the necessary strength. Next was the frame. The ribs were spaced much farther apart than in other ships of the time, sometimes a meter apart. This saved a huge amount of weight in timber. How could they get away with this? The strength came from the clinker-built skin of the hull itself. The overlapping planks, held together by thousands of iron rivets, created a semi-monocoque shell. Like the body of an insect, the skin provided much of its own structural integrity. And the ribs were there to provide shape and support, but they didn't have to do all the work. Then there was the way the planks were attached to the ribs. They were not nailed or bolted directly and rigidly to the frame. Instead, the Vikings carved natural wooden cleats or lugs on the inner face of each plank. Holes were drilled through these cleats and through the ribs. The two were then lashed together using tough, flexible rope made from spruce root. This created a strong connection, but one that had a small amount of give. It allowed the light, thin hull to flex and move, absorbing the shock of the waves rather than fighting against it. The result of all these techniques was a ship that was incredibly light for its size. The famous Gokstad ship, at 23 meters long, displaced only about 20 tons. A comparable ship from another culture might have weighed twice that. This lightness had profound consequences. It meant the ship sat high in the water, giving it a very shallow draft. It could sail in rivers and coastal waters that were inaccessible to heavier ships. It also meant the ship was fast. With less mass to push through the water, it could achieve high speeds under both sail and oar. A light ship is a responsive ship, but Perhaps the most important advantage of its lightweight was that the ship was portable. Not the whole ship at once, but it could be moved overland. The Vikings established portages, overland routes between rivers or around impassable rapids. They would unload the ship, lay down logs as rollers, and with the entire crew hauling on ropes, they could drag their own ship across miles of land to the next body of water. This gave them unparalleled strategic mobility. They could bypass fortifications, appear suddenly deep within enemy territory, and strike where they were least expected. The Frankish merchant saw an eggshell, Ragnar saw a weapon. The lightness of the Longship was a deliberate, calculated engineering choice that gave the Viking speed, access, and surprise. Number 7, the oar ports were a perfect, self-closing design. Finn was a young rower on his first long voyage. It was 995 AD, and they were crossing the North Sea in a longship named Fjord Drake. The wind had died, and for 2 days they had been rowing. Finn's hands were raw and his shoulders ached. He sat on his sea chest, which held his few belongings and also served as his rowing bench. His oar was a long, slender piece of pine passing through a hole in the side of the ship. This was the oar port. In calm weather, it was simple enough, but on the second day, the sea grew choppy. As the ship rolled, the oar ports on the lower side would dip beneath the waves. Finn braced for the gush of cold seawater that he expected to pour through the hole. But it never came. He looked closely at the oar port, and for the first time, he noticed its clever design. It wasn't just a simple hole cut in the plank, it was a circular hole with a vertical slit extending a few inches upwards. This keyhole shape was the first part of the secret. When it was time to row, the oar was passed through the circular hole from the inside. The blade, being wide and flat, couldn't fit through the hole, but the narrow shaft of the oar could be slid up into the vertical slit. This allowed the blade to be maneuvered outside the hull. Then the oar was dropped back down into the circular part of the port. The round shaft of the oar now filled the round hole almost perfectly, but there was a second, even more brilliant part of the design. On the inside of the hull, each oar port was fitted with a small wooden cover. It was a simple disc of wood, slightly larger than the hole, with a leather hinge on one side. When the oar was shipped, and not in use, this cover could be swiveled over the hole and latched, sealing it completely. The true genius, however, was how it worked when the oar was in use. The cover wasn't latched, it just hung loosely from its hinge. As Finn pulled on his oar, the shaft moved back and forth, but the cover was designed in such a way that the oar itself would push it closed at the end of each stroke. And if a wave hit the side of the ship, the pressure of the water from the outside would instantly slam the small wooden disc shut against the inside of the hull. The water's own pressure created the seal. A small amount might seep through, but the powerful gush that Finn had expected was stopped by this simple automatic valve. Finn realized that this small, seemingly insignificant detail was a marvel of engineering. It allowed the ship to have a full bank of oars, positioned low to the water for maximum leverage and power, without compromising the integrity of the hull. A ship with 30 oar ports per side had 60 potential leaks. Without an effective way to seal them, the ship would be swamped in any kind of rough weather. This design was also incredibly robust. There were no complex parts to break. It was just a wooden disc and a leather hinge. If it did break, it could be easily repaired by any crewman with a knife and a piece of wood. It was a simple, elegant solution to a critical problem. It allowed the Longship to be both a powerful sailing vessel and a formidable man-powered warship capable of operating in a wide range of sea conditions. Finn stopped thinking about his aching shoulders and looked at the small wooden circle by his feet with a newfound respect. It was a tiny piece of the ship, but it was one of the secrets that kept them all alive. Number 6, the ship's lines were carved by eye, not by plan. Olaf the Elder was the most respected shipwright in the district of Vestfold. It was the year 850 AD. He was old now, his back bent, and his hands gnarled like oak roots, but his eyes were still sharp. He was overseeing the start of a new ship. A young shipwright from a neighboring village, trained in a slightly different tradition, was helping. The young man, named Brand, brought with him a set of measuring rods and knotted ropes. He was ready to lay out the ship's dimensions according to a fixed plan. And Olaf watched him for a while, a small smile on his face. He let Brand measure out the length of the keel and mark the center point. Then he walked over and picked up a handful of small wooden pegs. He walked along the line. Brand had marked, and with his eye alone, he began to place the pegs, adjusting them slightly, stepping back, squinting, then moving them again. He was not measuring, he was feeling the shape of the ship. Brand was confused. "Where are the plans?" he asked. "How do we know the width, the curve of the bow?" Olaf gestured for him to come closer. He picked up a long, thin, flexible strip of wood, a batten. He and another experienced shipwright held the batten against the pegs Olaf had placed. The wood bent into a long, fair curve. It was the line of the ship's hull. "There," Olaf said, his voice a low rumble. "There is the plan." This was a fundamental secret of Viking shipbuilding. The ships were not built from rigid, pre-drawn plans or blueprints. They were created through a tradition of knowledge passed down through generations. This tradition was based on a system of proportions and a master shipwright's experienced eye. The shipwright knew that the ship's beam, its width, should be a certain fraction of its length. He knew the angle at which the stem and stern posts should rise. These were not written rules, but ingrained knowledge. The process was organic and iterative. After laying the keel, the stem and stern posts were raised. Then the first few planks, the garboards, were attached to the keel. From this point on, the shape of the ship was determined plank by plank. The shipwright would select a plank, shape it, and offer it up to the hull. He would clamp it in place and step back, looking at the line it created. He would adjust it, perhaps trimming a little more off one edge with his adze, until the curve was perfect. He was not forcing the wood to fit a drawing. He was letting the wood, and his eye, guide the final shape. This method, called shell-first construction, is completely different from later European shipbuilding, where a full internal skeleton was built first, and the planks were then forced to fit the frame. The Viking method allowed for incredible artistry and subtlety. Each ship was unique, its lines slightly different, a reflection of the master builder's personal style, and the specific qualities of the timber available. It also allowed for continuous improvement. If a shipwright found that a certain curve performed exceptionally well in the water, he would remember it and incorporate it into his next build. The designs were constantly evolving, being refined with each new hull that was laid. Brand learned more in that one summer with Olaf than in 5 years of following fixed measurements. He learned to see the flow of water in his mind's eye as he shaped a plank. He learned to trust the feel of the adze in his hand. He learned that a ship was not an object to be assembled, but a sculpture to be revealed. The longships were so famously beautiful, with their elegant, sweeping lines, because they were not the product of geometry, but of artistry. Their plans were not on paper, but in the mind and eye of the master shipwright. Number 5, the dragonhead was a piece of psychological technology. The year is 845 AD. A young monk named Brother Martinus is standing on the walls of a small monastery on the coast of Francia. It is a calm, misty morning. He is on watch, but his mind is wandering. Then he sees it. At first, it is just a dark shape moving silently out of the sea mist. It is low in the water, and it is moving fast, even though there is no wind. Then, the shape resolves itself. It is a ship, but like no ship he has ever seen. It is long, slender, and menacing. At its prow rears a monstrous head. It is a dragon, its wooden jaws open in a silent roar, its eyes painted with a malevolent glare. Intricate carvings of serpents and beasts writhe along its neck. As the ship gets closer, he can see the line of painted shields along its side, like the scales of some great sea creature. Behind it, another emerges from the mist, and another. A fleet of sea dragons coming for them. The psychological impact is immediate and overwhelming. Before a single warrior has stepped ashore, before a single axe has been swung, Brother Martinez is paralyzed by fear. This is not just an attack by men, it is the arrival of monsters. This was the intended effect. The iconic dragon head of the Viking Longship was not mere decoration. It was a sophisticated piece of psychological warfare. In an age of superstition where the world was filled with spirits and monsters, the Vikings deliberately crafted their ships to look like something that had emerged from a nightmare. The head was often carved from a single massive piece of wood. It was designed to be terrifying, combining features of dragons, serpents, and wolves. It was often painted in bright, garish colors to make it even more shocking, but the technology went further. The heads were often removable. According to Icelandic sagas and laws, a ship was supposed to remove its menacing figurehead when approaching friendly shores. The reason given was to avoid frightening the land's guardian spirits, the Landvatir. This practicality demonstrates that the Vikings were fully aware of the head's power. It was a tool to be deployed when needed. Approaching home or a friendly port, the head was taken down and stowed, and the ship became a simple vessel. Approaching a target for a raid, the head was mounted and the ship was transformed into a weapon of terror. The effect was amplified by the ship itself. The long, low profile, the incredible speed under oar, the way it could appear suddenly in a shallow river far from the sea, it all contributed to the image of an otherworldly predator. The sight of a fleet of these dragon ships appearing out of the morning mist on a previously safe river was devastating to morale. It was a statement of intent. It said that the men on board were not ordinary sailors or soldiers. They were men who sailed in the company of monsters, and they brought their monsters with them. For the crew themselves, the dragon head had a different but equally important function. It was a source of identity and pride, a banner for their ship. It connected them to the powerful beasts of their mythology. They were the crew of the sea serpent or the iron wolf. It gave them a collective spirit and reinforced their own fearsome reputation. When they rowed towards a shore, they were not just men in a boat, they were the body of the great beast whose head reared up before them. The dragon head was, in essence, a weapon system. It targeted the mind of the enemy, seeking to defeat them with fear long before the physical battle began. Number 4. The anchor was a tool for a quick getaway. Eric, the Red, stood on the shore of a small, sheltered cove in the land he named Greenland. It was late in the day in the year 986 AD. His expedition had made landfall. His 2 ships were now at rest in the calm water, but they were not moored in the way a modern sailor might expect. They were not tied up to the shore. Instead, they were anchored from both the bow and the stern. A small, simple-looking anchor was dropped from the bow, and a second, heavier anchor was dropped from the stern further out in the cove. The ships floated between them, their bows pointing out to the open sea. A young member of the crew named Torfi questioned the arrangement. "Why not just pull the ships onto the beach?" he asked. "They are light enough. It would be safer." Eric shook his head. "Safer for the ships, perhaps, not for us." He pointed out towards the mouth of the cove. "We do not know this land. We do not know what might come from those hills while we sleep. If we have to leave in a hurry, in the dark, we cannot waste time trying to push a beach ship back into the water." This was the secret behind the Vikings' typical anchoring strategy. It was all about a quick and efficient departure. Their primary anchor was often a simple stone, lashed to a wooden stalk to help it dig into the seabed, or a more sophisticated iron anchor with flukes. But their method of deployment was what mattered. By anchoring bow and stern, with the bow facing the exit, the ship was always ready to go. The process of leaving was a masterpiece of speed. A small crew could stay on the ship. On command, the bow anchor line would be cut or released. At the same time, the men on the stern anchor line would begin to haul. The ship would effectively be pulled backwards, out of the cove. by its own stern anchor. Once it reached the anchor, that line would be cut or the anchor quickly hauled aboard, and the men could get to the oars or sail immediately. The ship would already be pointing in the right direction, out to sea. There was no need to turn around in a confined space. This maneuver, called a kedge, allowed a Viking crew to go from a resting state to being underway and moving at speed in a matter of minutes. This was crucial for a group of people who were often in unfamiliar or hostile territory. Whether exploring, raiding, or trading, the ability to make a rapid, controlled escape was a matter of life and death. It meant they could camp on a shore with a greater degree of security, knowing that their escape route was literally rigged and ready. This technique also protected the ship. Beaching a vessel, even one with a shallow draft, always carried the risk of damage from rocks or a falling tide that could leave the ship stranded and strained. Anchoring in this way kept the ship floating in the safety of the water, away from the dangers of the shoreline. The anchor was not just a tool for stopping, it was an active part of their maneuvering and security system. It was another example of how every aspect of Viking seamanship was honed for maximum efficiency and tactical advantage. They thought not only about how to arrive, but just as importantly, about how to leave. Torfi looked at the two ships, floating silently, poised for instant flight. He understood, the ships weren't just resting, they were waiting. Number 3. The ship was designed to be carried by its crew. It was a hot summer day in the year 907 AD. Oleg, a Varangian chieftain, stood before the walls of Constantinople. His massive fleet of over 2,000 ships, according to the chronicles, had been blocked from reaching the city. The Byzantines had stretched a colossal iron chain across the Golden Horn, the city's primary harbor. No ship could pass. Oleg's men were sailors and warriors, not siege engineers. A direct assault on the land walls was a fool's errand. The campaign seemed to be at a stalemate, but Oleg had a secret weapon, the design of his ships. He looked at the narrow strip of land, the portage that separated the Bosphorus from the harbor. He gave an order that must have seemed like madness to the watching Byzantines. Take the ships out of the water! The Viking longships, even the larger ones, were built with this possibility in mind. Their light construction and shallow draft were key. But another less obvious feature was their smooth, rounded bottoms. They lacked the deep, sharp keel of later sailing vessels. The keel was present, but it was shallow. This made the ship less stable under sail in a crosswind, but it made it perfect for sliding over land. Oleg's men went to work. They unloaded the cargo from a number of ships to make them as light as possible. Then they laid down a path of logs, greased with fat, creating a makeshift slipway. With the entire crew of a ship, perhaps 40 to 60 men, hauling on ropes, they physically dragged the vessel out of the water and onto the log rollers. The smooth hull slid over the greased logs with surprisingly little resistance. The sight must have been astonishing to the defenders on the city walls. They saw a fleet of ships literally sailing on land. Oleg's men, chanting and heaving, rolled their ships across the isthmus, bypassing the Great Chain completely. They then relaunched them directly into the Golden Horn, inside the city's primary defenses. The psychological shock was immense. The Byzantines had secured their front door, only to see their enemy simply carry his boats around to the back. Faced with a fleet now inside their harbor, the emperor had little choice but to negotiate. Oleg secured a hugely favorable trade treaty without a major battle. This event, though perhaps embellished in the telling, highlights a core engineering principle of the Longship. It was a multi-terrain vehicle. It was not bound to a single river system or body of water. The Vikings routinely used portages to move between river systems in Eastern Europe, allowing them to travel from the Baltic Sea all the way down to the Black Sea. This gave them access to the riches of Byzantium and the trade routes of the Silk Road. This capability was a result of a series of deliberate design choices. The use of split planks for a high strength-to-weight ratio, the shell-first construction, the shallow keel. Even the placement of the ribs provided handholds for lifting and carrying. The ship wasn't just built for the water, it was built to be overcome the land. It was this, piece of engineering that allowed the Vikings to project their power deep into the heart of continents, far from any ocean. The ship was not just a boat, it was the key component of a revolutionary amphibious transport system. Number 2, the symmetrical design meant there was no turning back. The fjord was a trap. Einar and his crew had rowed their longship, the Sea Wolf, deep into the winding waterway on the coast of Scotland in 880 AD. They had been chasing a local chieftain, hoping to capture his settlement, but they had misjudged the tide and the terrain. They reached a dead end, a sheer cliff face, and as they turned, they saw the local warriors appearing on the cliffs above them, armed with bows and heavy stones. Worse, 3 of their ships were now blocking the narrow entrance to the fjord they had just come through. They were caught. Panic began to spread among the younger crew members. They were trapped between a rock wall and an enemy force in a channel so narrow that turning their 20-meter ship around would be a slow, clumsy process, exposing them to a hail of arrows and rocks. But Einar was calm. He shouted a single order to his steersman at the rear of the ship. "Rolf, to the bow!" Rolf, the helmsman, nodded. He secured the great steering oar at the stern. Then he did something that would have been impossible on any other type of ship. He walked the length of the vessel past the rowing men to the prow. The prow of the ship was identical in shape and construction to the stern. It was a perfect mirror image, and it was equipped with a second mounting block for a steering oar. The crew passed a spare steery, a reserve steering oar they always carried, up to him. Within a minute, Rolf had mounted the spare oar at the bow. Einar then gave the command that saved their lives. "Row! Backwards!" The men, without changing their positions on the rowing benches, simply reversed the direction of their strokes. The ship began to move backwards. But it wasn't moving backwards blindly. Rolf, now standing at the new stern, had full control. He was steering the ship in reverse. The ship that had been the bow was now the stern. The Sea Wolf shot backwards down the narrow fjord with the same speed and agility it had moving forwards. This was the genius of the symmetrical, double-ended design. The bow and the stern were virtually interchangeable. This had several profound implications. First, it made construction simpler. The complex curves of both ends of the ship could be made using the same templates and techniques. But its tactical value was immense. A longship never had to turn around. This was critical in the confined spaces of fjords, rivers, or crowded harbors. And it allowed for rapid retreats and redeployments. A ship could probe a dangerous channel and, if it met resistance, could immediately reverse course without a lengthy and vulnerable turning maneuver. The Scottish warriors on the cliffs were stunned. The ship they had trapped was now fleeing at full speed, but it wasn't turning around. It was simply moving in the other direction as if it had been designed to do so. They loosed arrows and dropped rocks, but the ship was a fast-moving target. Einar's crew, protected by the sides of the fjord and their own shields, powered the ship backwards. Rolf, at the now functioning front steering oar, skillfully navigated the channel. They broke through the surprised, blockading ships at the mouth of the fjord and escaped to the open sea. This feature was unique to the Viking-style clinker-built ships. It was a design philosophy that prioritized versatility and tactical flexibility above all else. A longship didn't have a dedicated front or back. It simply had 2 ends. Which one was the bow and which was the stern depended entirely on which way the ship needed to go. There was no such thing as turning back, only choosing a new forward. Number 1, they split the log to follow the soul of the wood. It was the first lesson. Before a boy named Ulf could even touch an adze or a hammer, the old shipwright, Geirmund, took him to a single, colossal oak log. It was a perfect specimen, felled weeks earlier, over 1 meter in diameter and arrow straight. This log, Geirmund explained in his quiet way in their Danish shipyard in 820 AD, would become the planks for a new longship. Ulf assumed they would take it to the saw pit. He had seen Frankish merchants with ships built of thick sawn planks. Geirmund shook his head in disgust at the very idea. "A saw is a butcher's tool," he said. "It murders the wood. We do not butcher the wood. We persuade it." He then showed Ulf the true method. He and another man used iron wedges and heavy wooden mallets. They didn't start at the edge of the log. They drove the first wedge directly into the center, into the heartwood. With a series of dull, powerful thuds, the wedge sank in. And soon, a tiny crack appeared. They drove more wedges into this crack. The sound changed from a thud to a deep groaning. and then, with a great tearing sound, the entire log split perfectly in half. This was only the beginning. They took one of the halves and, looking at the grain on the split face, they began to split it again. This process was repeated, always working from the center out, splitting the log into thinner and thinner wedges like slices of a giant cake. This technique was called radial cleaving. It was infinitely more difficult and time-consuming than sawing, but it was the most important secret of the Longship's construction. Gearman picked up one of the final pieces, a rough wedge-shaped plank. He showed Ulf the grain. The lines of the wood fibers ran perfectly from one end of the plank to the other. "Look," he said. "When you split the wood, you are not cutting the fibers. You are following the path they grew in. You are following the soul of the tree. The strength of the oak is in these long threads. A saw cuts across them, and the strength bleeds away. When we split the wood, all the strength remains." So he was describing the microscopic structure of the wood. The long cellulose fibers bound by a natural polymer called lignin are what give wood its strength and flexibility. By splitting the log along its radial lines, they ensured that these fibers remained unbroken for the entire length of the plank. The resulting plank was, for its weight, far stronger, more flexible, and more resistant to rot than any sawn plank could ever be. This meant they could build their ships with planks that were incredibly thin, sometimes only a single inch thick, without sacrificing the integrity of the hull. This was the key to the ship's lightness, which in turn was the key to its speed and portability. The technique required a profound understanding of wood. A shipwright had to be able to read the log to see the internal lines of stress and growth, to know exactly where to place the wedges to achieve a clean split. It required perfect, straight-grained, knot-free old-growth timber, which is why the Vikings valued the great oak forests so highly. This was the foundational secret, the one upon which all the others were built. The flexibility of the keel, the lightness of the hull, the strength of the clinker skin, none of it would have been possible without the extraordinary properties of radially split planks. It was a technology that was in complete harmony with the nature of the material. They did not impose their will on the wood. They released the form that was already hidden within it. Ulf never forgot that first lesson. A longship was not made of dead wood. It was made of the preserved strength and spirit of a living tree.